So let's hope this is working. Let's hope this is working. It's my first live stream in my life, so I hope we're not getting into any technical problems in here. Let's see. Got the chat open. Let me see if I can take a look. At the actual, is this thing actually live? I think so. Should work. Let me open it up. Any technical? Yeah, cool. So maybe let's. Yeah, cool. Thank you. I see the chat is working as well. That's nice. Thanks everyone who's actually joined the live stream. I've got on a secondary screen my Qiskit Slack, and we can also then take a look at the comments there and stuff like that. So, but also have the live the YouTube live chat as well, which is pretty much real time. So, as I said in the about 15 minutes ago in the comments, I think it would be cool to do it sort of two ways, right? So on one side, basically, I'll go through the material myself, and then you can follow live and also interact with me live via the chat in YouTube Live if you want. But we can also then, if you prefer to do it on your own pace, we can also then meet in about 90 minutes from now, and then have a sort of a more Q&A and discussion as well. I know Sam did it with Zoom, which kind of feels like it might be a better space for the discussion in the last 30 minutes, but we'll see. I wanted to kind of try and see if the YouTube live thing would work end-to-end as well. So, and feedback at the end, it's always super welcome. Let me see. Let me just put this here. Okay, perfect. So, I'll go and start right away. If you've got any questions, any comments, feel free to interrupt me. I mean, the chat is on, so I can read that stuff as well. And there might be a bit of a delay, I think, but it shouldn't be much of an issue. And I hope you can see my screen as well here. So I've got basically three things open up because I thought that would be useful to have Qiskit open as well, just if there's some circuits that we can play with quickly. I mean, I know it's about Qiskit, and I'm trying to learn Qiskit and see how can I quickly use it as well for these kind of things. I'm probably a bit spoiled because I'm too much used to Quirk right now, but that's why I have both open, so I can see really how it feels to interact with Qiskit almost like real time. So we'll cover the same that Sam did. So basically, section 0, but I'll just go through this fairly quickly because it's most of the first 2 points is, I think, installation and stuff like that. This is something that I've gone through myself in the past week. It took me a while to actually get Qiskit running on Windows because of Python compatibility issues, but I managed to do it, so should be fairly simple. And then we'll try to go through section 1, quantum states and qubits. I think they try to cover until 1.4. We'll see how far we get there. But this is something that I haven't done, so I've skimmed through the book when it was released, and I've come across it a couple of times here and there, but it's not. I'm doing it first time as well, so I'm really curious about this. Cool. So let's go ahead with the with section 0. I mean, this is an introduction to Python. I'm not a big coder myself. I studied computer science, and I did do, my own take of Java, C++, and stuff like that. Python I touched a little bit, but basically what I read this week, this is more of a sort of a really quick Python introduction in terms of the language and notation concepts like lists, the fact that lists can contain any mixture of variable types, lists index from 0, what else? Tuples. I found this interesting, the concept of a tuple in comparison to lists, in the sense that the major difference is that you cannot. So the tuple is items can be changed in the list, okay, but not the tuple. So I'm not so sure how much this. I guess this is useful because you can use tuples as keys for maps as well. But we'll see. The section, it does not relate to quantum computing in and of itself and to Qiskit match. So it's hard to see how those things will be useful, but it's definitely a good section to have to then come back to when you feel that you need it. What else was in here? So the loop, to loop over range of numbers. Note that this starts at 0 by default and ends at n-1 for range n. Those are sort of details that you should keep in mind when you're probably coming across problems debugging your code. Those are typical things. If and elif and else statements. I mean, again, feel free to go through these on your own pace. I'm mostly gonna skim through these, I think. NumPy is interesting. I haven't really used NumPy a lot myself, but basically it comes and it basically packs some of those mathematical functions that would just come in handy, like the sinus and stuff like that. Do some maths. Okay, definition of functions. I guess I'm always sort of having this issue between how useful it is to use a programming language to build circuits when you're just playing with it at a really small scale versus like a big scale. That's why I have both things open in here. Because I personally, but it's my thing, I personally tend to get stuck too much on little code issues, but it's just something that I probably can get used to better. So what is next? We've got the basic Qiskit. Okay, syntax installation and stuff like that. So now there's something we can play with in here. So let's go. I think I'll try to make this a little bit bigger so you can see this better. And I'll try to, in this section, type in rather than just copy paste, although it's really tempting. But I think that if I want to learn Qiskit, I should the actual act of typing definitely helps you get into those things sort of wired into your brain, especially if you're not used with the language. So the rest of the section is intended for people who already know the fundamental concepts of quantum computing. It can be used for readers who wish to skip straight to the latest chapters in which the concepts are put to use. Yeah, let's go through these. I think I'll just quickly skim through these, but it's basically the basics of how you draw circuits and stuff like that. So if you're listening to these and watching these and you're not really familiar with any quantum computing concepts, I guess don't worry, we'll come into these fairly quickly. So let's start by importing these from Qiskit. Import everything. And then the object at the heart of Qiskit is a quantum circuit. So here's how you create one, and we'll call it QC. QC equals quantum. Another thing that I realized is that I have one of those Dell laptops that have a webcam at the bottom of the screen, and that's a really interesting design decision because you can see my giant fingers as I type. Quantum circuit. Cool. So it's currently empty. To make the circuit less trivial, we need to define a register of qubits. So again, there's not a lot of background information here in why you should use registers and why not and stuff like that. So it's just so you get the basics of how you use Qiskit. So we'll get to that at some point, I hope. So you can create a quantum register for object. For example, let's define a register consisting of 2 qubits and call it QR. So we'll call it QR quantum register 2, and we'll call it. So this needs sort of a name. Okay, that's its option. Okay, that's optional. Now we can add it to the circuit using the add register method and see that it has been added by checking the keyrex variable. Yeah, so I'll add it to the circuit. Add register QR and QC QREX. So that should basically, okay, so that outputs the register that I have. Let me see if I can, okay, I have too many windows open on my secondary screen. So, good. What else? Now, okay, so now let's draw this. I've seen that in other videos of people reviewing Qiskit, and I found it pretty cool that you can actually just do this, and it prints it like in instead of terminal mode. It's pretty cool. It gets fancy when you've got all the like fancy circuitry in here, but you can basically also do draw. Oh, what am I doing? QC draw output equals MPL, and that basically gives it a nice shape. That's cool. So they're ready. This is just naming. So applying. Okay, so let's go ahead. Applying gates. To make something happen, we need to add gates. For example, let's try the Hadamard gate. Like the H gate is the Hadamard gate. And so that's supposed to give us an error. Yes, because it's missing a required positional argument, which is probably the qubit that we want to apply it to. Yeah. So it can be individually, there's a typo in here, addressed as QR0 and QR1. So because QR is the quantum resistance, so you can basically say, or you should probably do something like this, and then say we want to apply to the qubit 0. Is that what the tutorial says? Yeah. Okay, so this is just an output that you have to ignore according to the book. When the last line doesn't have an equal sign or semicolon, then it just outputs what's there. We can also add a control node using the CX, and then this requires 2 arguments. Okay, so and then you do it this way. So you basically do QC CX. Quite a lot of concepts introduced in a really short amount of lines. So it's definitely going to be tricky to remember a lot of this stuff. So if you do that and then you do QC draw output equals MPL. So thanks. So reading the chat as well as I can. I'm not really good at multitasking, but I'll do my best. Thanks for showing the ASCII hack drawing for quantum circuit. I personally use it all the time. Yeah, it's I saw this randomly in one of the video tutorials from Sentex, which I found it pretty cool because I mean I knew about Qiskit before, but I really had never played with it, and I think it's just nice. It's faster to type, but I guess it can get quite complicated if you have a big circuit. So let's see. Okay, so and it's pretty nice. The way this looks like, cool. Now state vector simulator. We're now at the stage that we can actually look at an output from the circuit. Specifically, we will use the state vector simulator to see what is happening to the state vector of the 2 qubits. To get this simulator ready to go, we use the following line. Okay, that's a more complicated line. Vector simulator get backend, and now we're gonna do state vector simulator. So and so that gets us the so in Qiskit we use backends to refer to the things on which quantum programs actually run. Simulators are real quantum devices. To get a job for a backend, we need to set up the corresponding backend object. So the simulator we want is defined in part of Qiskit known as IR, I don't know how to pronounce. By giving the name of the simulator we want to the get backend method, we get the backend object that we need. And so you can also list the possible backends. Okay, backends. Yeah, so chasm simulator, unitary simulator. Okay, interesting. All of the simulators are local, meaning that they run on the machine on which Qiskit is installed. That's good. The IBM Q user, so using them on your machine can be done without signing up to the IBM. I don't know if this is supposed to be the IBM Q, signing up to the the IBM Q user agreement. Running the simulation is done by Qiskit's execute command. So you basically create a job like this. Execute QC vector simulator. And so that gives you the job and then you can get the state vector. So I guess where this is going, because I didn't really, when I went through this, I didn't really go through the actual, I didn't actually do the coding part. So now that I'm doing this at a slower pace, vector, and so for amplitude in cat, print the amplitude. I guess what this is doing, yeah. So this is the vector for a Bell state, which is what we expect given the circuit. Exactly. That's the one of the simplest ways to create entanglement. And I guess for those used to other graphical tools, this is the equivalent of, I mean, those are the amplitudes that you get when you do something like this in Quark, for example. Those are those amplitudes. So here you've got like 0.7 plus 0i. In this case, Quark uses I as the imaginary notation, but Qiskit is using j. I think that's a never-ending discussion between physicists and mathematicians. But basically, you've got like a 0.7. This is amplitude 0 and 0, and this is again plus 0.7. So yeah, I don't know why it doesn't say 0 plus 0j. But I guess it's fine. So that's this. Okay, so you can create also while we're having a nicely defined state vector, we can another feature of Qiskit. It's possible to initialize the circuit with an arbitrary pure state. What's that? So you create a new quantum circuit and then you initialize it with that state. Okay. So you're basically doing new QC equals quantum circuit QR, new QC initialize cat. So what's happening here? Cat QR. So cat is our state vector. So you actually need the state vector, not the amplitudes. You need the actual state vector object. Yeah, because the amplitudes are just the amplitudes. You're not having the phase information in there, I guess. New QC. And sorry if there's someone who does not really have any basic knowledge of quantum computing, and some of those comments make no sense, then they'll make in the next, and I guess in the next hour or so, and in the next sessions. Let's go with this one. Casting complex values to real discards the imaginary part. What does this mean? That's interesting. Is it initialize? So complex warning. I like that, complex warning. So casting complex values to real discards the imaginary part. Yeah. Okay, but this did happen when I initialized, or so what if I say new QC2, new QC2, so what if I just, okay, quantum circuit QR, and now new QC2 initialize, and I do cat QR. Okay, no, it actually, this is, but is this a warning? I don't know. Yeah, it's a warning. It's a complex warning. New QC2 draw. So, okay, now I get no warning. That's interesting. New QC2 draw output equals MPL. I mean, I'll take that, I guess, is something to take a look at later as well. That doesn't render super nicely. Well, at least not as nice as here. maybe because of the screen, the viewport size. Or so if I do new QC2 draw output MPL yay, output NPL, yeah, doesn't so okay. Anyway, that was an awkward complex warning. Let's move on. So I'll note that as question for later. Classical registers and the QASM simulator. So in the above simulation, we got our state vector. That is now what we get from a real quantum computer. For that, we need measurement, and to handle measurement, we need to define where the results will go. So the reason this is because it's not. Maybe it's not the goal to explain it here, but I think it deserves a mention. At least that the reason you can't get all this state vector data is because, I mean, it's the idea is that you actually would have to sample that circuit to get the data, right? Like you can't simulate it, because you can't simulate at some point if you've got, like, 100 qubits. It's just too much information that you can't encode, because you need like 2 to the power of 100 to actually pieces of information that you have to encode. So that's why you can just take a look at these. That's why simulators and little toy tools like this one allow you to take a look at these things, and that probably helps you to design or test concepts for your circuits and your algorithms. But then when it comes to really scaling it, and this is where my never-ending internal discussion about how much math do you really need to understand quantum computing kicks in, because from one side, it's like for toy examples, you don't need. You probably can get quite far with just intuition. But if you think about scaling an idea to 100 qubits or 1,000 qubits, then you probably need to do actually some ninja math magic to make sure that actually works, right? Or trial and error, but it can be maybe not the most efficient thing to do. But anyway. Okay, so now we define classical registers. This is where we're going to put our measurements, I guess. So CR equals classical register to CREG, not QREG, because that's just a name, right? And then QC at register CR. So you got that, and what if we now say QC draw? So you've got now the 2 classical qubits here at the bottom. Classical bits, not classical qubits, obviously. And now you can basically say measure from the register 0 to the classical register 0, qubit 0, and from the quantum register, the 1, basically then do this, put the measurement in the classical one. So let's take a look at this measure. Measure QR 0 to CR1. And again, that might feel like I'm going really slow, but it's like, for me, that's helping me a lot to understand. Hi, Valid. I see the comments. And Pawan V Nayak. Thanks. Thanks for joining. So that's definitely helping me. What am I doing? That's definitely helping me sort of internalize the actual, how Qiskit actually works. Because not how it actually works, but how it can actually be used. So, yeah. Okay, so now you got those lines in here, so this means this measurement is going to go, yeah, perfect. How can I undo that? Yeah, that doesn't work. Nice. Okay, so I messed it up. That's an interesting idea. So how could I revert that? Is it possible to revert that? Like, if you add measures, if anyone knows, let me know, because that's now basically messed up. So I don't know if I could well, I can just go here and then kind of re-execute the whole thing, right? Can I just do that? Run. Can I just run everything? But not where I messed up, obviously. So this is going to be 1, no, 0, and this is going to be, yeah, that's correct now. Okay, now I got it right. But I don't know if there's a way you can just, yeah, maybe it doesn't make any sense from a usability perspective. I mean, you just rerun your program now, because we're doing it interactive. It's difficult to correct those things otherwise. And what does it look like if I just say qc draw output equals MPL? So yeah, so now you have a nice diagram in here, nice circuit that it looks like exactly like this one. So it's cool. And basically now we can run this on a local simulator whose effect is to emulate a real quantum device. For this we need to add another input to the execute function, which is the shots. And because basically every time you're going to run the circuit, you're going to get just one of the results, so you need to run it many times to get basically a the statistics of what the result would be. If you don't provide any shots, it gets a default value of 1024. So we're going to do emulator add get backend. Get backend, and this is going to be the chasm simulator. And we're going to create a job, execute qc the emulator, and we're going to emulator, and we're going to say shots 8192. Yeah, I'll see if I can. Okay, maybe, because I don't know. I feel I'm typing at the bottom end of the screen, and that's probably not helpful for people who are watching. So maybe that's going to be better, and I'm going to put the quirk actually at the bottom of the screen. That should make it easier. And now I can get the histogram values. Okay, so the counts, job, result, get counts. So again, I don't know. Okay, so because this is a lot of stuff packed into just some lines. So you're getting a backend, you're executing the job, and you've got a bunch of things inside the result object. So you can get the counts, which I get is, okay, so it's basically a map with how many times you've got this output and how many times you've got this output, right? And of course you can use that to then create something nice like this. But we've seen above, you can also get the state vector. But again, I think you can only get the state vector if you use the state vector simulator, not the custom simulator. I guess that's the idea, but we can try. So what if I say get state vector? Does this work at all? No, that doesn't work. So the simulator is not set up to give you these, the chasm simulator, right? Because this is simulating. I think this is probably the idea. Is it's simulating an actual device, and so you in theory you wouldn't be able to get those things, this type of information in a device. So that's, you know, okay. So but if we, instead of that, we say get counts. Now we get, so if I print, what am I doing here? So if I print these, I'm getting that, and note that it's slightly different than what you get here. So this model has some sort of maybe randomness in it, like noise model. I don't know how to call it, but it doesn't behave always in a deterministic, or in a way that it looks like deterministic. So that's nice. And then so you can, for us to use plot histogram, we need to import that from visualizations. Okay, so from Qiskit visualization import, I'll just import everything and then say plot histogram hist, and that should give us that nice thing here. Perfect. That's cool. Okay, so for compatible backends, we can also ask for and get the ordered list of results. So you get the get memory. So what if I samples equals job result get memory? I cannot get it here. Oh, I have to activate memory true, otherwise it doesn't save it. Okay, so if I say shots here and I say memory equals true, and I go through all that, and now I do this, and now I have it. So if I print the, why it keeps going back to the search. If I print the samples, that's going to be a lot of samples though. Okay, yeah, that's interesting. That's cool. I mean, I don't know exactly why would this be helpful right now, but I'm guessing it has a usage at some point. So note that the bits are labeled from right to left. So the CR0 is the one that's the farthest right. Yeah, I keep having problems with that. Also, when I use Quirk, that qubit in here, it's so that's Q0, and that's basically the one on the rightmost. Yeah, so here they follow the same convention, so that's good. I mean, the reason this is helpful is because you can directly use that as binary representations of numbers. So this number exactly, which is 2 to the power of 7 days, yeah, so it's 8,192. So now that the bits, okay, as example of this, here's an 8-qubit circuit with a Pauli X on only the qubit number 7, which has the output stored in the bit number 7. So, yeah. Okay. Simplified notation. So, multiple quantum and classical registers can be added to a circuit. However, if we need no more than one of each, then we can use, okay, so you don't have to specify, because up here we're specifying a register, then adding the register to the quantum circuit, and it's a bunch of stuff that it's kind of giving you overhead. But if you want to quickly test some things, then you can just go ahead and say, okay, QC equals quantum circuit 3, and that assumes probably that it's 3 3 qubits. And okay, you can also do the Hadamarts like that, so you can do directly on the on the circuit Hadamard, and then you specify the qubit, and then if you draw it, you QC draw, then you get that. Okay, cool. Default names and stuff. Yeah. Okay, and then the second, and here I'm guessing that's going to be the classical register. So, so if you say QC, or we'll use the same QC 2-1. Okay, so now you've got one classical register here. Good. To see this in action, here's a simple circuit. Note that when making a measurement, we also refer to the bits in the classical register by index. Yeah. So if I now say QC, okay, let me create it from scratch. QC quantum circuit 2-1, and now QCH0. That is the Hadamard. Then a control X, that's what we're doing all the time, between 0 controlled on 0 to the qubit 1, and then we do a QC measure 1 to 0. So I guess that means the classical register. And if I now draw, it's definitely much easier to draw it like that. You don't have to type the yeah, so now you got that. Okay, cool. Creating custom gates. That's interesting because this is one of the things that back then when I was using the online tool, the Composer, I was playing with custom gates, and it was really difficult because you couldn't really create a lot of stuff in there. it was kind of a lot of the things were like, you know, pending or coming soon. But I'm guessing Qiskit comes a bit better equipped with that. So as we've seen, it is possible to combine different circuits to make bigger ones. We can also use a more sophisticated version of these to make custom gates. For example, here's a circuit that implements a control X between qubit 0 and 2 using qubit 1 to mediate the process. So you've got that in here. And then, to instruction. Okay. I think, so let's give it a try. Subcircuit equals quantum circuit 3. Do I need to name it? Toggle X, toggle CX. And then I do subcircuit. It's a bunch of control X between 0 and 1. Oh, come on. Between 1 and 2. I probably can just... it's quite obvious I haven't been coding for a while. So you can now do 0, 1. I could have copied the whole thing, and 1, 2. And now we basically sub-circuit, we draw it, and that should give us this. And so now you can, okay, so you can turn that into a custom gate by calling the to instruction. Okay, so toggle CX equals subcircuit to instruction. Okay, interesting. And now basically you can append it. So you can append it. Okay, so you create a quantum register for a new quantum circuit with this quantum register in it, and now you append it to the quantum circuit, toggle CX, and you basically have to, okay, so you've got to actually tell what qubits from the register are used as inputs to that circuit. And now new QC. I'm gonna draw it with the MPL because I guess it's MPL math plot leap or something like that. I guess that's where it comes from. So, okay, new QC append. So, what have I done here wrong? What it says, name new is not defined. Oh yeah, it's new QC. Cool. Okay, so that's all you get. Now it renders better than here. Cool, perfect. So accessing on real quantum hardware. Oh yeah, so this is something that I'm not gonna cover now, and I'll probably cover in the next session because I haven't been able to go through these basically. So I think the idea here is you can now actually use real quantum hardware. So you basically you have to sign up to the IBM to have an IBMQ account, and I have one that it's pretty crappy, and I wanted to kind of have a clean start. So I'm gonna, if you don't mind, I'm gonna skip that here, and I'll try to get this in the next session. There's one interesting thing here, if I remember well, which is about noise models that I don't wanna. I wanna make sure that I don't skip. But basically, you can use real devices. Where was that? You can construct a noise model to mimic. I found this extremely cool. Like when I read that, I was like, oh, I didn't know you could do that with Qiskit. So you can basically take take a device and kind of copy the properties and create a noise model that mimics that device, and then use it in your emulator. So the idea here is that then you know, for testing purposes, you can get as close to a real device as possible. And that's actually, I think that's really cool, because using a real machine, it's, you know, sometimes it might take time because you're in the queue. And I mean, we give it for granted that IBM gives access to all those machines, but you know, I'm not sure for how long, if this is going to be always for free, or, and so that it's really helpful, the fact that you can simulate the noise in there. So it's been already, now we're like 40 minutes in, so it's been a pretty step-by-step part. Now that I've actually gone through the coding, I feel it's definitely super intuitive to build circuits. So far at the level we've been doing it, right? So you have registers. You make the operations directly on the registers, on the qubits. You can initialize stuff in here. One thing maybe that I'd say confused me a bit is I don't see, for example, I found extremely useful in Quirk that you can see the phases in this with this circle notation, and so you can see this little bar here rotating. And intuitively, when you work with, when you try to understand circuits like, for example, the QFT, which I guess we'll get to by session 3 or so, or session 4, I don't know, because there's all the algorithms are packed in here. I doubt we can cover all that session in one, so I think we'll probably be doing 1 or 2 algorithms per session max. But once we get to the quantum Fourier transform, for example, which basically gets into, you know, into a lot of those rotations, I'm curious how we're going to do this with Qiskit, because that's not, it doesn't help me to build intuition in terms of how is the interference going to play, you know, and it's not always about, because I can't, maybe it's just that I'm missing intuition in terms of mapping those things out to particular rotations. I don't know. We'll see. But that's one thing that I'm kind of looking forward to see how we deal with it. So if no one else has any questions right now, then I'll just quickly skim through the linear algebra part, which I did go through as well in preparation for these. It's the only. This again is the only. The section 0 is the only one that I went through in preparation for these, and then we can jump to the quantum states and qubits part as well. So I'm not a big fan of maths, and I think if everyone who, if any of you has been watching some of my videos, you probably know these. It's not that I'm bad at maths. It's just I don't feel they are. I feel they bring some overhead in trying to understand some things which could be understood intuitively. Now, you gotta take that with a pinch of salt, because basically if what you're doing is proving stuff, then you definitely should use mathematics as a formal way and formal language to proving things. But the maths that you need for quantum computing, I think it's you know, it's different when you talk about small scale and big scale. So for small scale and just the basics, right? You talk about vectors and vector spaces. So I read through these. Again, I'm not going to read line by line now, because I think that's going to be really heavy. And you can do that at your own pace as well. Maybe, you know, maybe we will not be the full hour and a half. We'll see. So you have some time to go through these, or you can do this through the week between now and the next session. But I think I can maybe give some feedback based on what I remember after reading these. So in overall, this is really well done. So in terms of the other stuff that I've read, other tutorials that I've gone through, and also what used to be in the IBM Q experience before, which was I think some sort of earlier version of these. This is way more mature, and I think it's focused to the points that are really needed. So vectors and vector spaces. Here, I think the section introduces the notion of a vector really from scratch for someone who has no idea what a vector is. Now, of course, did some maths myself, right? I mean, like everyone who's done some formal training in that or whatever, or gone to high school. I mean, you know, I don't know. It depends on the country and the education system. I don't know when people get introduced to vectors in mathematics, but if you haven't seen that, I'd be interested to know what's the experience in trying to understand this. But it's vectors, vector spaces. But you know, how do you add vectors? How do you multiply vectors by a scalar? Matrices and matrix operations. I think it's good that the section focuses on seeing matrices as sort of rotations or as sort of transformations. That's something that I first came across when, you know, back in high school, got introduced to the notion of you know, 2D and 3D transformations, and then you're basically using matrices to encode those transformations, and that kind of made a lot of sense to me. So I think this is a really good way to explain that. Let me maybe just quickly scan these. Applying matrices and vectors. So we manipulate qubits in our quantum computer by applying sequences of quantum gates, and as it turns out, it can be expressed as different matrices that can be applied to a state vector, thus changing the state. So the Pauli X gate is one example that's used in here. I think, you know, introducing the notation is also well done. And there's some of this stuff in here later on. Let me see. So conjugate transpose. Again, it's like I started getting into quantum computing about half a year ago, and I think notations and concepts like the conjugate transpose, Hermitian, unitary, and stuff like there's a point in time in your learning journey that they will come up as like, maybe now I should really understand that, but it's not. It didn't feel like something you kind of need every day to get you know, ramp up quickly on understanding quantum circuits. But you might need that at some point. So I'm not saying that you shouldn't care about this maths. You should. But it's not. It's my personal opinion. I don't believe it's so critical and core, unless you're planning to do some kind of formal research and then you want to prove certain things on papers. So I think the session goes through the inverse matrix, how to calculate stuff like that, and calculating the inverse matrix is really important in quantum computing, since most of the matrices deal with our unitary. Yeah, so then you can calculate the inverse by doing what was that? The inverse, okay, the conjugate transpose. Yeah. I found this also really interesting, the whole concept of spanning sets, linear dependencies, and bases. But again, it's one thing that I personally think, and it's my personal opinion, right? So everyone who's following this at their own pace will probably see this differently. You can trust that this has been well proven and just go on with it. In terms of, you know, basically the whole point of this is how do you define a basis, a computational basis, and why is that important, and what are the properties that actually help us into you know, exploiting the notion of a computational basis in quantum computing. Linear dependency. I wanted to get the inner product. So I think that it is one of the things that I really liked from. Oh, wait a second! You can plot the Bloch vector like. Oh, you can do that. Wait a second. Can you do that? That's cool. Plot Bloch vector. Oh, nice. Okay. And how can you plot an arrow into this? Just with a state vector? Wait a second. So what was the state vector? I had this. We had this at some point, right? Get backend. Get state vector. Oh yeah, but we must have, I think. Oh no, that's in ket. So I think we didn't override that. So if I do plot Bloch vector, let's see if that works. No. is it that you need some specific format, like you just need the coordinates actually? So what if I say, I don't know, 0, 1, 0. Yeah, okay. That's cool. That's cool. The surface of this, not sure for how long I was offline. I hope that you guys didn't lose me. Oh my god, yeah. It seems like I'm back at being live. I hope so. You can plot by adding the values for x, y, z, such as plot block vector. Yeah, thank you. I didn't see that for some reason. The whole thing went offline. I don't know, but I think you must see me. You must be able to see me now already. So, cool. Let's go ahead. I mean, this is something that I'll try to play with as we get into the gates. I have to note that, so I have to basically remember this. Let me see. So just want to make sure this is really perfect. So thank you. For how long was I offline? I mean, I'm sorry for that. I didn't see that. It didn't even warn me at all or anything. So anyway, let's go back to these. So eigenvectors and eigenvalues. So consider that this is also an interesting section, but it doesn't. A couple of minutes, no worries. Okay, thank you. Cool. So okay, I feel I gotta back up a little bit. So we talked about these, something to play with as well, and then eigenvectors and eigenvalues. So this is a notion. This is a notion of. Yeah, people say just plot the blocks here. Okay. So what I was saying, just for the people who maybe disconnected and now are back online. I basically was on a tangent to trying to basically say that the points that are not in the surface of the Bloch sphere, they are also somehow valid states, and they pop up when you basically have sort of entangled states. So here you can see that that those points are not touching the surface. It's probably difficult to see, but that's what I was talking about, and that's what I wanted to basically test. But it would require me to go and use other gates that we haven't introduced yet. So I'm just I didn't want to do that for those who really because I'm not sure if there's anyone who's just getting into these. So I didn't want to get too much into that. I don't know myself how to do these kind of things in Qiskit. So good. Eigenvectors and eigenvalues. Consider the relationship of this form. Now, so just to make sure that we use the rest of the time to move to move past the section 0. This is a notion that this is a part that is well introduced in here, but I feel that there is missing a bit of a disconnection to it's missing a bit of the connection to the actual usage in thinking about circuits and stuff like that. I found this comes in handy when you're doing simulations and stuff like that, like chemistry simulations and things like this, because basically it says that lambda is some number, and these numbers are basically sort of characteristic to the matrix that they belong to. And so if you multiply, blah, 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 so here's how to calculate that, and then the so you've got that equation here, and 0. Yeah, I don't know. I feel this is a bit just kind of like a short introduction to that, but it's not something that I felt it was helping me at all when I read through that. And I'm still not feeling super confident with eigenvectors, and I know it's probably pretty basic, but it just didn't feel like, I don't know, it didn't feel like a good part of the section. The matrix exponentials, though, I have to admit, it was interesting to to go through these. I also recommend you take a look at three. How is he called? I think it's in YouTube. YouTube 3. I think it's like 3 blue, 1 brown, and he's got I mean, he's got a video on eigenvectors and eigenvalues, which is really cool, and he's got also a video on he's got a video on the Euler equation, which explains the concept of, you know, what does it mean, the E at all. Can't find it now, but yeah, something like this here. So and this definitely helps you understand what is E. So definitely go through these videos. This helps you understand a lot, that even in mathematics, and that was really eye-opening for me, that even in mathematics, different concepts can be interpreted differently, right? So, and here I think there's one sentence. Let me see if I can find it. Yeah, so it basically says a matrix inside of an exponential seems super weird, right? But the whole point is you can interpret this in different ways. You can interpret this as rotations. You can interpret this in different forms, and that's really helpful. So I don't know. I didn't find like those two sections brought me anything as a newcomer, if you kind of would be a newcomer to quantum computing, but they're definitely good to know that they are there to come back to if needed. So this is my whole point in this section, basically. And I know some people might just like to go through the basics, through the mathematical basics really well through, but it's not my style. So that's, and sure, it might probably bring some problems later on, but that's basically it for, I think, for the section 0. Python and Jupyter notebooks. So basically, you know, as I said, basics of Python. It walks you through, installing Anaconda. I had some issues with the version of Python, but I got it to run finally. I think this has been the most useful introduction to Qiskit ever. I mean, it's the fact that it's here in the section 0 really helps. It just gets you through the basic notation and functions and how you would build circuits and stuff like that. And I'm hoping that we will be building on these in the next parts of the book. So. Good. So it's about 10. So we've got half an hour. So then we also have 30 more minutes at the end to basically do a bit of the discussion on the chat if you guys want to. But we can just quickly go through. We can get started with the quantum states and qubits section 1. I also want to take a look quickly at in the Slack. There hasn't been any questions in here, but if you feel like if you're going this on your own pace, but anyway, you're probably not listening to this if you're doing so, you can also put the questions in there as well. Good. I think for these, I'm gonna make that a bit bigger so you can see this better in the screen, because I think there's not much coding in the first part. So let's go. Let's go through these. But I mean, here's to my point. I didn't even start reading these, and again, I haven't gone through these, right? So I'm a first timer as well. So, but if I'd like to build that circuit, like it feels like it's going to cost me a hell lot of time to do that in Qiskit. But again, this is just maybe a lack of practice. Just for playing around with circuits, I think a graphical editor is comes in much more than handy. But I mean, the IBM Q experience has also the how's it called, the composer, which maybe we can take a look at actually. See if it's gonna be a bit dirty though, because I have a bunch of I have it here bookmarked. So the IBM Quantum Experience. So signing with Google, I don't know. I guess so. I'll take that off the screen for a second because I don't know if there's going to be anything in here. Oh no, it's signed up. Okay, perfect. Then we're good to go. How can I bring that back now? Okay, whoopa. Sorry. So okay, so here we are. I'm gonna maybe try to use that the composer in here to kind of do some of the things in here. So Wait a second. So you can also build. Yeah, exactly. That's what I'm doing. Cool. Yeah, I just saw the. I'm just reading the comments now. That's what I'll do, because I think it makes a lot of sense, because it's gonna have also a similar experience with what's in here. So, and a lot has changed since I first tried this composer, and I see there's a bunch of stuff in here that was not here before. See a new design for the gates. And yeah, what I liked a lot is that you can kind of also edit with OpenQASM, so you can quickly say if you don't want 5 qubits and you want to just stick to 4, that's what we have here. Then you can easily tweak that and then have it here updated. So that's pretty cool as well. Okay, so if you think quantum mechanics sounds challenging, you're not alone. All of our intuitions are based on day-to-day experiences, and so are better at understanding the behavior of balls and bananas than atoms and electrons. Though quantum objects can seem random and chaotic at first, they just follow a different set of rules. And so once we know these rules, we can use them to create new and powerful technology. That's nice. So to get you started on your journey, let's test what you already know. Which of the following is the correct description of a bit? It's a bit awkward that the circuit is in here, though. I feel like I would like to start building it, but I don't know. I guess that's a half adder or something like that. I think it's adding stuff. So what is Huang saying? You can store OpenQASM code in a string variable like this. Oh, you can do that? Then let's give it a quick try. That's nice. So if you do this, I'm just how do I build a control? Okay, so control not like that, control not like that. Can I? That is okay. So I should probably. I think it was like that. I don't know if that still works. Yes, and then a TOEFL gate, and I should change that to Q3. Perfect. So, and now we've got two measurements, Z measurements. One goes in here, and another one goes in here. So you're saying you can actually, so I can actually go here, copy the whole thing, open the Jupyter notebook. Maybe I'll do a new notebook, Python 3. So from Qiskit, import everything, and basically, so what are you saying? You're saying that you can store OpenQASM code in a string variable like this. QASM equals your QASM code. Okay. So something like QASM equals, and now I can just do that. You're saying. Should probably escape this, shouldn't I? Or is it just this? Maybe it's just this. Let's give it a try. Maybe I think that should simply be all a string, right? That's what we're saying here. So, oh, come on. So I can import it as a string like that, and now it's all a string, but I'm not sure if I should get. So let's see if that works, and then you can say from this is quantum circuits from QASM string to convert quantum circuits. Okay, so if I now say QC equals quantum circuit, and I guess you do this, and then you say from. I have no idea. I've never seen that before, so I'm probably not doing it correctly. But so from quantum string, and now I pass it the QASM. Is that? Maybe I'm missing the this part include. So, but maybe I can replace that by single quotes. Or I can replace that by single quotes. Or I can just escape that, probably. Can I just do that? I think I messed up something now. should say inc. So if okay, that's worked. Cool. And now if I do QC draw, maybe I also gotta add this. You know, it's empty. We'll see. But maybe I can take a look at the documentation for that. But that would be that would be kind of a cool thing. Oh no, that's a this looks like the right link. So how does this work? If I search for these QASM string, take in a QASM string and generate a quantum circuit from QASM string. How to use it though? Okay, it returns a quantum circuit. Ah, so it returns a quantum circuit. So actually, really? Ah, so it's a static method. But then I don't know. So is it just returning me another? Is it just returning me another? Yeah, cool. It works. Nice. Okay. Interesting. Nice. If I say QCC draw output equals MPL, yeah, that's nice. Beautiful. Okay. So okay, that's definitely helpful. Thanks for the tip. That's definitely helpful because then you can play basically with this stuff in here, and then kind of quickly get that into your code. Okay, that's nice. Perfect. But I guess my whole point here is why to have a language that allows you to build circuits, right? I mean, is it because you want to build them programmatically? I mean, that's the idea, right? And so the way you would build them programmatically is because you're maybe doing something where you're testing different variations of the circuit, especially when you do variational things where you want to test how a certain different gates affect the output and stuff like that. I guess that's how it becomes in handy. But okay, at least it's good to know you can build it here and then take it into Qiskit like that. So let's go ahead. That was another tangent. So to get you started on the journey towards quantum computing, let's see what you already know. So which of the following one is a correct description of bit? A blade used by a carpenter. The smallest unit of information, either a 0 or a 1, something you put into a horse's mouth. I'd say it's the second one. Although I have no idea if bit is also they're all correct. It's a very multi-purpose word, but if you chose the second one, it shows that you are already thinking along the right lines. The idea is that information can be stored and processed in a series of zeros and ones. It's a big conceptual, quite a big conceptual hurdle, but it's something most people today know without even thinking about it. Taking this as a starting point, we can start to imagine bits that obey the rules of quantum mechanics. These quantum bits, or qubits, will then allow us to process information in new and different ways. So in the first section, so the intent is for the broadest possible audience. You won't see any math that you didn't learn before you were age 10. We'll look at how bits work in standard computers and then start to explore how can you do things in different ways with qubits. After reading these, you should already be able to start thinking about interesting things you try out with qubits. So we'll start diving deeper into the section, into the world of qubits. For these, we'll need some way of keeping track of what they are doing when we apply gates. So that's so that's basically the Bloch sphere. This chapter will mostly be effective for readers who are already familiar with vectors and matrices. Okay, and then if not, go to this section, and we'll be using Qiskit, so you can also get an introduction here. Okay, that's good. Let's go ahead to the next section then. The atoms of computation. So let's take a quick, let's skim this quickly through first. So you've got basically splitting information into bits. So this seems to be an explanation about, we'll just read that. We'll go ahead and read that in a second. So this seems to be an explanation of numerical systems, base 10, and I guess it's the idea is to introduce then base 2. Computation as a diagram, okay. So you've got, so that's the diagram for adding, right? A and B, I think. And here you've got the diagram that we built there, so it's the quantum version of these. So we're going to build the first quantum circuit. Okay, okay, sounds cool. Looks interesting. Encoding an input, okay. And yeah, encode. That's cool. So you can. Oh, well, no, that's nothing new. Okay, so it's just telling you the qubits. I thought you were encoding something special, but remembering how to add. Okay, so that's. I guess this through this section seems like we're going to be building a circuit to add qubits. Cool. And step by step. That seems interesting. Cool. And then we've got basically the final circuit. I think that's a cool way to get into these, and sort of recap the stuff, you know, how you do that with Qiskit and how you build a circuit with Qiskit. Let's see. But it's really from scratch, right? So it's basically, so programming a quantum computer is now something that anyone can do from home. But what to create is, you know, what is a quantum program anyway? In fact, what is a quantum computer? So these questions can be answered by making comparisons to standard digital computers, which unfortunately many people don't actually understand how they work. And in this article, we'll look at the basic principles behind these devices to help us transition over to quantum computing later on. We'll do it using the same tools for quantum. So now I'm gonna do here. Okay, so it's just, okay, no, I don't even need to copy that. That's basically, there's also an import of from Qiskit visualization, import everything. So we're ready. And then splitting information into bits. The first thing we need to know about is the idea of bits. They're designed to be the world's simplest alphabet with only 2 characters, 0 and 1. We can represent any piece of information. One example is numbers. In European languages, numbers are usually represented using a string of 10 of the 10 digits from 0 to 9. And in this string, each digit represents how many times the number contains a certain power of 10. For example, when we write 9,213, what we mean is 9,000 plus 200 plus 10 plus 3. Yeah, that's a... Okay, so that's something that I think it's a nice way to... It's definitely really for a broad audience, because that's something that I think most people that... again, I don't know. Maybe it's too broad of a statement to say most people who have programmed anything in their lives are able or kind of to understand this notion, or they know this. But yeah, so you can emphasize that as the powers of 10. So it's 9 times 10 to the power of 3, 2 times 10 to the power of 2, and I think that's the I mean, that's the way you can. That's why you call it a base 10, because your base is 10 digits from 0 to 9, and so the binary in the binary case, your base is 2 digits, 0 and 1, and then you build up from there. Okay, this is the one based on the binary number system. For example, is based on number 2. This means using 2 characters 0 and 1 to express numbers as multiples of powers of 2. In which case, 9,213 becomes this huge string in here. Okay. And so is in terms of powers of tool. The strings known as binary strings can be used to represent more than just numbers. For example, there is a way to represent any text using bits. Yeah, I think this is the... Oh, what? What happened? So it seems I was again offline. I'll definitely have to check my my connection. I have a more stable connection for some reason. That didn't seem to work well. Okay. Now we're back online, and I think that time was really short. So apologies for this. Good. Let's see. The unique properties of qubits. That's where we were. No, that's not where we were. We were in the atoms of computation. Cool. So, and this is a. Let me refresh. Now. That doesn't seem to. This table doesn't seem to either work or. I don't know. But I guess it's a table of how to encode strings with so characters mapped to numbers, and then you have the corresponding binary representation of these. So yeah, I think we'll kind of skip through that now and then go back to computation as a diagram. So whether we're using qubits or bits, we need to manipulate them in order to turn the inputs we have into outputs we need. For the very simplest programs for a small number of bits, it's useful to represent these processes in a diagram known as circuit diagram. You have inputs on the left, outputs on the right, and the operations in the middle. So these operations are called gates, mostly for historical reasons. That's interesting, actually, why they're called gates. I don't know. Here's an example of what a circuit looks like for standard bit-based computers. Yeah. Okay. And so for quantum computers, it looks like this. The rest of the section will be to explain how to build circuits, and at the end we'll know how to create circuits above the circuit above, what does it do, and why is it useful. Good. Let's get started with this then. See if I can again put myself, sort of put this a bit upper in the screen. Hope everyone's seeing that. Yeah, seems to be all fine. Live stream is going on. Yeah, perfect. So, yeah, back online again. Had another small network issue. So we've got like about 10 minutes left. I'm gonna go maybe through the first part in here, and then we can have a quick break, and then think about whether there's any questions, any discussions, and if not, I mean, I can also use the rest of the time to go through some other things and ideas, and then we'll leave it there, and you can complete the rest of the section during the week between now and session 2. But let's get started with this. So we've got basically n. Okay, so first we'll focus on the last of these jobs. We start by creating a circuit with 8 qubits and 8 outputs. 8 qubits and 8 outputs. N equals 8. N qubits equals 8, and n bits equals 8. And then QC output equals quantum circuit NQ and NB. This is what we've seen in the first section. Basically, if I now go through the external qubits and quantum is done by an operation called measure. Okay, so it feels a bit like, this part feels a bit like you're repeating some of the stuff that you read there. So if you've done this fairly in a consecutive way, like we're doing now, it feels a bit like of repeating stuff. If I now draw the circuit, I should get that part in here. Yeah, cool. That's cool. Qubits are always initialized to give the output 0. Since we don't do anything to our qubits in the circuit above, this is exactly the result we'll get when we measure them. Yeah. So, and now let's see if I can type that. So counts equals execute the QC output, then AR get backend chasm simulator result get counts and then plot histogram counts. Okay, so we get the same thing here. So what we've done is we've executed that with the chasm simulator and get the results basically. So it feels a bit of a bit repetitive if you've done that before, right before the other chapter. The reason for running many times and showing the result as a histogram is because quantum computers may have some randomness in their results. In this case, since we're doing anything quantum, we get just this. So note that this result comes from a quantum simulator, which is a standard computer calculating what quantum computers would do. So you can do these with a real device like that. Yeah, it feels. Let's look at. So it feels a bit repetitive. Let's look at how to encode a different binary string as an input. For this, we need what is known as a NOT gate. This is the most basic operation that you can do in a computer. It simply flips the bit value 0 becomes 1 and 1 becomes 0. For qubits, there's an operation called X that does the job of the NOT gate. So, okay, so now we're creating another quantum circuit, a separate one. Okay, why are we doing it in a separate one? Oh, I think I know where this is going. Quantum circuit. I think maybe, because now we're using N, so that's what we have here. Okay, so maybe we're gonna then plug in these and kind of have that as a measurement circuit, and then just plug it in and glue the two circuits together. Interesting. Could be encode QC encode X into the qubit 7. And now we're gonna do QC encode draw. We're definitely gonna use this output equaling MPL and see that we get that thing with the X with an X gate at the very end. Extracting the results can be done using the circuit we have before. Oh, that's cool. Okay, that's interesting. You can do that. Okay, so you create another circuit where we just concatenating them. Okay. Encode plus QC output. That's cool. QC draw. What is justify? Why does it say justify no? What if I say output MPL? What if I just say that? And what's the difference if I just say now justify none? There doesn't seem to be any difference to me. But it'll be interesting to know why. Okay. Now we can run the combined circuit and look at the inputs. So we'll just copy paste that. It feels like, okay, so now we get that, which is okay, which is correct. And yeah, so okay, so what have we really done now? I mean, we've basically, okay, so we're building just again building circuit basic stuff. It feels, yeah, okay, so far it feels a bit repetitive. I know I've said that already many times, but so the bit we flipped, which comes from qubit 7, leaves on to the far left of the string. This is because Qiskit numbers and bits string from right to left. If this convention seems too odd to you, don't worry. It seems odd to a lot of you people, and some prefer the number that beats the other way around. I don't know. I think I prefer the way this is specified in here. So flipping this, now okay, to the power of 7. This is the number 128. Now we try another number for yourself. You could do your age, for example, just use a search engine to find what your number looks like in binary, and then add some zeros to the left side if you're younger than 64. Okay, but basically, okay, so this is another now QC encode quantum circuit. Okay, that's another example. Okay, it's again, it's 10:30. I almost feel like I could spend 10 more minutes and skim through these quickly, so we get at least done with this. Because it feels, I mean, at least to me, it's kind of a really, really basic introduction. But if you definitely need to go through that in a slower pace, just go through this because it's definitely helpful. But I mean, what else is in here? So it's how to add, right? So I think the way this is going is, okay, so the algorithm for adding is you add 3 plus 4, and then you you might carry something. In this case, you don't, right? So you keep doing that for the rest of the digits, but then when you have 2 plus 8, you have 10. So basically, here you need to carry the one forward to your next step of the algorithm. So that's simple addition, and then this seems to go through the same, but for binary, where it's like whenever you're going to have 1 plus 1, you're always going to carry something with you. So yeah, 1 plus 1 is 2, but in binary is 1, 0. So that one you need to carry, and that's the reason you build this in here. So adding with Qiskit, let's make our own half adder. I'm just going to go, as I said, I'm going to go ahead, I'm going to go for like 10 more minutes, and then we jump into discussion. For 10 more minutes, I'm just writing this in Slack, and then leave space for discussion, just so we can close the current section. Yeah, so now that we're back at it. Okay, so let's make our half adder using Qiskit. This will include a part of the circuit that encodes the input, and the one that executes the algorithm, and a part that extracts the results. I kind of like to approach this in this modular way, where each of your circuits is actually a separate circuit object, and then you can glue them together. That's an interesting construct. The 2 bits that we want to add are encoded in qubits 0 and 1. So in this case, it's 1 and 1, right? The result will be a string of the 2 bits, which we will read out from qubits 2 and 3. Okay, so here's the result, and then you encode it, and then you extract it to the classical register. The basic operations of computing are known as logic gates. We've already used the NOT gate, but this is not enough to make our half adder. We could only use it to manually write out the answers, but since we want to computer to do actual computing stuff, computing for us, will need some more powerful gates. So this is the result. Okay, so these are all the possible results. Then to get this part of solution correct, we need something that we can figure out whether the 2 qubits are different or not, because that's what if you want to know whether you need to carry, then that only happens when you've got 1 plus 1. So there's the XOR gate in classical computing that does that. Since that's quite a long name, control not. Qiskit is the name, is the CX, which is even shorter. So you've got that circuit for a QC for a control not. Yeah. This is applied to a pair of qubits. One acts as a control, and the other one as a target. So if this qubit is 1, then the qubit 1 gets flipped. Another way of explaining the control not is to say that it does a not on the target if the control is 1 and does nothing otherwise. Yeah. So try the control not out for yourself by trying each possible input. Okay, so if you execute this circuit, you'll find that the output is 1, 1. Because you turn that into a 1, and then there's a control here, and then that turns it into a 1, so the output is 1, 1. So for a half adder, we don't want to override one of our inputs. Instead, we want to write the results on a different pair of qubits. For this, we can use 2 C0s. Okay, so now we get into explaining that that part of the algorithm. That's okay. So that's what you're doing is you're basically putting the output into Q2, right? So if you're so if this is a 1, then you're gonna flip here because Q2 starts off as 0. So if Q0 is 1, then Q2 is gonna become 1, and then if Q1 is 1, then you're effectively flipping this back to 0 because you're adding it, right? So it's 1 plus 1 equals 1, 0, and so the Q2 should be 0. But then what you're missing here is that in this case, then you're gonna have to have the carry. So how do you know that you need to carry? You basically, I guess you could do it this way. Do it 2 ways. One is basically having a control knot. That's the TOEFL gate. I think it's introduced later here. Exactly. But I was also wondering, couldn't you just use the qubit tool? Wouldn't that work as well? If it's 0, so it's not a control anymore, but like a control on 1, it's a control on 0, then that signals that you need to carry as well. Well, no, that's not true, because if you've got 0 plus 0, then this is 0, so that shouldn't that should not then trigger the carry. Yeah, that would be a mistake. You know what I mean? So if you do something like let me take that like that. If instead of these you're doing something like this, but that's not helping you, because if you've got 0, 0 in here, then you would trigger the carry qubit as well, and that's not what you want. Definitely not what you want. Okay, so but that's basically it. Back here. Okay, so let me make that small again. So we're now halfway to fully working half adder. We just have the other bit of the output left to do, the one that will live on qubit 4. If you look again for the 4 possible sums, you'll notice that there's only one case where you have a carry, which is 1 plus 1. Yeah. So, and this is to calculate this part, we could just get our computer to look at whether both of the inputs are 1. If they are, and only if they are, we need to do a NOT gate on qubit 4. That will flip it to the correct value. For this, we need a new gate called a C0, but controlled on 2 qubits. So CC0, or it's called TOEFL. For those who you're familiar with Boolean logic, it's an AND gate. Oh yeah, actually, right. Okay, so you've got the circuit in here. And then you get the results. Yeah, and that's the result 1, 0, right? Because 1 plus 1 is 2. So the result is 1, 0, which is the binary representation of the number 2. Yeah, and that's it basically. Yeah. Okay, cool. So let's do the following. I mean, I've gone through this fairly quickly, but we can now have a short Q&A of like 30 minutes or so. Maybe using the chat in live. I'll just put it in Slack now. If anyone wants to join the Q&A/discussion, you can go to the live stream right now. And then we can use the chat. I know it's probably not the best. It's definitely not. It's not the best format in comparison to an actual voice discussion. But let's see how this works. Let's see if people have any questions or not. And even if it's not related to that, we can also discuss other quantum computing related stuff if you guys feel like. So we've basically managed to go until 1.2, and you know, what I would suggest is that for those who want to join the next session on the following Sunday, you can work through the rest of the chapters or the sections, the subsections, and then at the beginning of the next session we'll do a recap on these. Basically, I'll go through it myself as well, and then give my feedback. And you can also ask questions if there was any problems in directly in the Qiskit Slack channel. And then any feedback in terms of the format is also really welcome. It's for me both the first time that I broadcast the live stream ever, and so I had to do a bit of a technical setup in here that I didn't have, but I think that's gone pretty well. Let's see. Okay, cool. But next session we'll focus on section 2. But let's jump into Q&A a bit maybe. Let's see how many people we got in the stream. So it says 3 concurrent viewers right now. I don't know how much this is live. I don't know. Is there anyone who has any questions that you wanted to discuss? If not, we can definitely use the time and take a look at some of the other stuff and skim through all the sections. We'll see. So use the chat if anyone has any questions. Yeah. Let me see. Too many things open, definitely. It was definitely for me it was interesting to go through the actual Qiskit part, but it felt as feedback a bit repetitive. So going through the 0.2 and then going through the atoms of computation felt a bit almost like the same kind of building circuits. There's definitely one thing in here that I hadn't seen and I find useful in terms of notation. That's the way you can add bits, you can add portions of a circuit together. Exactly, this here. This was useful. Yeah. So in terms of feedback, that's basically from what we've covered. That's it. And maybe I can use the rest of the time, it's like 15 minutes or so, to just go through. I'll skim the other sections. Let's see what we've got in here. Let me zoom that in. But if you have any questions, feel free to interrupt me. I'm gonna take a look at the chat in a more prominent way right now. But let me zoom that in. So in this section we covered basically the basics of building a half adder and so a circuit that adds numbers, and that's nothing really quantumish, I would say, but it at least helps us understand the basics of how to build a circuitry and what those things mean. So that's good. Then if we go to the 1.3, the unique properties of qubits, what are we talking about here? Heisenberg's uncertainty principle. Okay, at home with the Heisenbergs. I can't find my car keys. You probably know too much about their momentum. That's a good joke. That's a good joke. So what else is in here? So take a look at measurement. Okay, circuit composer looks like that, and then there is the small z. So see here, there's a measure underscore x y. Okay, so okay, that's cool. So this is going to be a, give me a second, I lost all my stuff in here right now. Yeah, for you nothing changed, I hope. So, but I just lost the chat. Okay, here it is. So this is basically, I think what this is going to be about is talking about the different measurements and the stuff that you can measure, because this is just a z measurement. But you can measure a qubit from different perspectives, right? Based on your computational basis. So you can measure it from, you can measure the x observable, you can measure the y or the z observable, and I think the way you do that is, measuring x means you should apply a Hadamard gate to your qubit or to your set of qubits. And then measure z. So it's the equivalent here would be you take the whole of your circuit into the I would say the x dimension, and then you measure z. That's going to give you the measurement from that perspective. And then there is, okay, here's measurement z. Okay, so that's okay. That's cool. I see. It's a pretty nice way to introduce that. But I wonder whether that's not confusing for a newcomer, though, to talk about this stuff that early. measure x. Okay, then you've got RI rotation on the y, so results for a y rotation. Okay, and measure z, and then measure x. So you can see that the results are somehow inverted. Okay, Einstein versus Bell, and I guess here, okay, so here there's an explanation of the Bell experiment, right? Where Einstein tried to prove that basically there must be a hidden variable or hidden information that kind of tells the qubits how to behave in terms of measurement or when they are measured. And so, you know, I think what this experiment proves is that there is something that's not true, right? Okay, that could be interesting. So basically, this is about measurement, measurement X, measurement Z, and this Bell experiment. Then 1.4 is about writing down qubit states. So what have we got here? So the Z basis. So this is about, okay, so here we go back a little bit into talking some notation and mathematics. And I wonder again whether that cannot be, whether that's not going to feel a bit repetitive if you've gone through the math part. The X basis part 1. Interesting. The Born rule. Oh, that's what I meant, right? So it's a way you can express mathematically what it means to so what it means to measure something, right? So the probability of getting 0 of that particular ket, and then mathematically you do the inner product, and that's what you get. Yeah. And the probability of this ket measuring 0 is 0, because then that's what you get in here. Okay. Okay. Global and relative phases. Vectors are how we use math to represent the state of qubits. Then we can calculate the probabilities of all the possible things that could ever be measured. This is equivalent to multiplying the states. Okay, so we're talking about relative phase in here. I think it will be interesting to see how this concept is introduced. The states plus and minus. Again, I'm just quickly skipping through this because we're not going to have time to cover all that. But you can do that on your own, and then we can do a quick recap at the beginning of next session. Oh, complex numbers. So I found it interesting that they were not introduced in the math part, in the math section, in the section 0, right? But that's going to be an interesting part as well. So okay, so this seems to be basically an introduction to notation. Get used a bit more to notation and to the mathematics about how you write the states. Good, and then you've got. I think that's where some session ended. Haven't seen the recording. I don't know if it's up already, but basically then you've got the Pauli matrices and the Bloch sphere. Those are two other things that maybe to stick consistent with the other sessions. This is where we will take it from, I think, because that's the already scope for the next session to start here. So I'm not gonna touch this. I would say, but I see some of the expectation value notation in here, so I'm interested. It will be interesting to know how much this is covered and how does this whole thing look like. Oh, so we've got blocks here again. Okay, yeah, but basically, okay, so basically that's it so far. I mean, I don't know what you guys think. It doesn't seem like there is. Let me see. Anyone who's maybe not because completely new to quantum computing, but it's I would say if you think about section 0 and 1, here my feedback would be it's a pretty much, I think it's a good introduction up to what I've seen right now. It seems to be repetitive in some points, but it gets you up and running with Qiskit fairly quickly. Now it's a hell lot of material without getting into any kind of quantum stuff. But again, that's just I'm probably biased and spoiled by the fact that I already know stuff, and so yeah. But I think that will be it. So, but I see there's section 3 is where the I would say really big challenging stuff is in here. We take a look at actual algorithms and we break those algorithms down. How does this look like? How have they done this? Quantum teleportation. Okay, so it's really codey. Nice. Okay. Well, can be interesting. And on a real machine as well. So I should probably set this up. So it's really codey. It's actually interesting because a lot of people approach it mathematically, and well, at least I thought that. Let's take a look at other stuff. The Deutsch user. So there's a question: do you find the bell test part difficult? I haven't gone through this. I haven't gone through the particular text myself yet, and we really didn't make it, I think, here. So this was in 1.4. So Huang is asking. Sorry, because I don't seem to be able to pronounce your first name correctly, but he's asking in the chat whether the bell part is understandable or not. I guess I'll give you feedback once we do the second the second part, the second session, because I haven't gone through this. This was here, right? So yeah, Einstein versus Bell. I mean, but we can try to go through this maybe. Let's see. We have now played with some of the features of qubits, but we haven't done anything that can be reproduced by a few beats and random number generator. You can therefore be forgiven for thinking the quantum variables are just classical variables. This is essentially the claim made by Einstein, Podolsky, and Rosen back in 1935. They objected to the uncertainty seen in quantum mechanics. They thought qubits should always know what output is. That's the thing I said about the hidden variable. No one spoke of qubits back then, and people hardly spoke of computers, but if we translate the arguments into modern language, they essentially claim that qubits can indeed be described by some form of classical variable. So it took until 1964 to show that they were wrong, and J.S. Bell proved that quantum variables behaved in a way that was fundamentally unique. Since then, many new ways have been found to prove these, and extensive experiments have been done to show that this is exactly the way the universe works. We'll now consider a simple demonstration using a variant of Hardy's paradox. Okay, so this is, I guess, the part that you're asking whether it's difficult to understand or not. So let's take a look at this. For this, we need two qubits set up in such a way that their results are correlated. Specifically, we want to set them up such that the following properties, I guess, are observed. If Z measurements are made on both qubits, they never both output 0. Okay, so they never agree. No, they could agree on 1, 1. Okay, they never both output 0. If an X measurement of one qubit outputs 1, a Z measurement of the other will output 0. So there is a correlation here between an X measurement and a Z measurement. This is okay. This is it feels like it needs to be. I would need to read this 2 or 3 more times to make sure I grasp that. But let's go ahead. If we have qubits that satisfy these properties, what can we infer about the remaining cases? For example, an X measurement of both. Okay, so this is going to be now running through this and see if we get any contradiction or something like that, probably. For an example, let's think about the case where both qubits output 1 for an X measurement. By applying property 2, right, we can deduce that the result would have been what the result would have been if we had made Z measurements instead. we would have gotten an output of 0 for both. Okay, let's back up for a second. Okay, so let's think about the case where both qubits output 1 for an x measurement. So, and then we apply property 2 and say if an x measurement of one qubit outputs 1, the z measurement of the other will output 0. Okay, so here it says both qubits have measured 1 for the x measurement. This means that in this case, this means that actually the other two, it means that according to these rules, right, it means that the other two both should output 0 in a z measurement, because here it says if one qubit outputs 1, the z measurement of the other will output 0. So if both qubits output 1 in x, it means that, you know, for qubit 1 it outputs 1, so it means qubit 0 when you measure z will output 0, and qubit 1 when measured in z will also output 0, which violates that statement, because it says that both can't never measure 0. Okay, so we would have gotten an output of 0 for both, yeah. However, this result is impossible according to property 1. Correct. That's what we just said now. So we can therefore conclude that output for 1 for x measurements of both qubits must also be impossible. Correct. The paragraph you just read contains all the math in this section. Don't feel bad if you need to read it a couple more times. I mean, you need to definitely read this carefully. So now let's see what actually happens. Here's the circuit composed of gates you will learn about in later sections. It prepares a pair of qubits that will satisfy the above properties. I mean, it's... Okay, so it prepares a bunch of rotations. It's a bunch of rotations and control Z gates. So it's not, there's no explanation on why this does it, but then let's see. Okay, so let's see in action. The first Z measurement of both qubits gives you, yeah, so that's, so there's no 0 0. I mean, I'm assuming, again, I'm not gonna copy paste that now, but if that's correct, then this is respecting the property 1. Yeah, let's see the results of an x measurement of one and a z measurement of the other. So results for the two x measurements on qubit 0 and z measurement on qubit 1. So, but what was again the if the x measurement of one of the qubits is 1 on x, is 0 on z. If it's 1 on x here, yeah. So the only possibility that doesn't pop up here is the 1 1, because that would invalidate the property 2. So the probability of 1 1 is 0. So you'll see if you swap around the measurements, this qubit is therefore also satisfy property 2. And now let's look at an x measurement of both. And okay, and so we can see here that 0 0 actually has got, so we reasoned that given properties 1 and 2, it would be impossible to get the output 1 1. Yeah, in both x, and nevertheless it's 0.09 probabilities of getting 1 1, so that's definitely okay. So where did it go wrong? Our mistake was in the following piece of reasoning. By applying property 2, we can deduce what the result would have been if we had made a z measurement instead. We used our knowledge of the x outputs to work out what the z outputs were. So once we'd done that, we assumed that we were certain about the value of both, more certain than the uncertainty principle allows us to be. Okay, I think that's the bit that's a bit complicated to grasp. So our logic would be completely valid if we weren't reasoning about quantum objects. If it was some non-quantum variable, that would the x would indeed be both well defined. So I guess what this is saying is that you can't. So what you can't infer, like these types of properties don't hold. Like you can't do that. If an x measurement like is 1, a z measurement will output 0, because what you're saying, this property is a property that it's, what you're saying in here is that you're, or the other way around, with that you're saying that both will measure 1. It's like you're making, yeah, you're assuming you know stuff about both measurements, and that's against the uncertainty principle. So you're basically saying, an uncertainty principle is telling you that you're gonna have, if you've got certainty somewhere, you're gonna have uncertainty on the other side. So if you know exactly what you're gonna measure with an x measurement, then you really don't know what you're gonna measure with the z measurement. So there's uncertainty there. And so despite the fact that you have a well-defined system, so you know in terms of uncertainty at that level you have a well-defined system, but you can't still infer a concrete measurement on the z if you don't know. So I think, again, I think that it's not too difficult to understand, but I'm again might be biased because I've gone through a similar explanation or similar experiments in other blogs and articles, and you just have to think about this twice. And especially there's that bit of not being intuitive, the fact that you can't infer two certainties from two different dimensions. That's like the x and the z one. That's the bit that's a bit kind of, I think, awkward to understand. It's a bit hand waving. So to explain Hardy test with uncertainty principle is a bit hand waving. I prefer a more traditional approach to explain with Bell inequality. I don't remember how the Bell inequality is explained, so I can definitely look that up. But it's one of these things that even if you don't understand that in the first run, but you just assume it's true and then go ahead and then you come back to it after after a while, then you're like, oh, now I understand what it means, right? So, but I can understand that for someone who really hasn't touched any of those concepts, that might be really complicated. So, but no, I mean, in terms of writing and in terms of the way this is explained, I think it's a pretty good job. So. Okay, cool. So the 2 hours are gone. Really, it's like 11, and I think that was a bit. I would say, from my perspective, I wanted to do that anyway at some point, to read through that. So I'm happy that I hopped on the opportunity to volunteer for these, and I'm going to keep running the next sessions as well based on the schedule. But definitely any feedback on the format is welcome. I haven't seen any questions in Slack, and I'll try to make sure that I have a more stable internet connection next time, so I don't, or at least I realize when things go offline, and so I don't lose people. But so far, if I have to summarize my experience with the first section 0 and section 1, they feel good. I would say they feel good. I can be picky, right? You can always say, this is a bit repetitive, or here and there you could do better, but it really feels overall a good introduction to the topic. And at the same time, you're learning Qiskit, which is really handful as well. It comes in handy as well. So I think the tricky part will be when we start talking about quantum circuits and quantum algorithms. This is when stuff gets complicated. Like when you move past the 1 qubit, that's when things get complicated. So, I mean, it seems like taking a look at these, you go from really basic stuff, and then suddenly quantum algorithms, and then suddenly applications. Like that's like VQE simulating molecules. That might be like a big jump. So we'll see. Thanks for sharing the session. Yeah, I like this format during the 1 hour, but maybe the discussion session should be Zoom. Okay, yeah. I agree. I think the discussion could be put into a more into another medium where you can have a more one-to-one voice discussion or many-to-many voice discussion. I think that's a cool format as well. So we'll try to set it up for next time. Thanks for the feedback. That's really welcome. Cool. Done. Then I'll leave it here. And thanks everyone for joining. And again, go through through the stuff that we haven't covered. Share feedback. And happy to receive any feedback from this session as well, as I said. So thank you very much, and we'll see each other on Sunday next week. Now it's time to close this. Bye.